Welcome everyone. Let's study today about critical velocity of a satellite. Student, you all know that artificial satellite are revolving around the Earth in a particular orbit. Okay, and for this orbit, the critical velocity is given to the satellite to revolve around the Earth in a particular orbit. And today we will see the derivation of a critical velocity. And this topic is for class 10th SSC and less from lesson space mission, and this is part 2 video of this lesson. Let's study. Alright, so this is a formula for critical velocity which we are going to derive it. Alright, so orbits of an artificial satellite. Student, all artificial satellites do not revolve in a similar orbits around the Earth. So depending upon the function or type of a satellite, the orbit of the satellite are different. And the function of the satellite decides the height of the satellite. Now the function means we know that we have studied different types of a satellite in our previous video, like communication satellite, broadcast satellite, navigational satellite. So depending upon the particular satellite, the height of the satellite is decided. And the nature of the orbit, like orbit will be whether it will be circular or elliptical, and whether the orbit shall be parallel to the equator or making some angle with it. So different orbit we will study in our next video. And to put the satellite in its proper orbit at a specific height above the Earth's surface, the satellite is taken to that height using a satellite launchers. Now satellite launchers means we have seen that GSLV, that is geosynchronous satellite launch vehicle, and PSLV, that is polar satellite launch vehicle. So these are the different satellite launcher. And then the satellite is given a specific velocity known as a critical velocity in a tangential direction to the orbit, and the satellite then starts revolving around the Earth. Alright, now let's derive the formula for critical velocity, that is VC. So student, here it is a picture showing orbit of an artificial satellite. So in this picture you can observe the pink color dot, that is a satellite, and this satellite is revolving around the Earth, and this is called as a satellite's orbit. Okay, and here blue color circle, this is the Earth, in which capital R is the radius of the Earth. Alright, and small r, this is the radius of the satellite from the center of the Earth. Alright, so if a satellite of mass m is revolving around the Earth in an orbit of height h with a speed vc, then so student, here small m is the mass of the satellite which is revolving around the Earth above the surface of the Earth with a height small h. Okay, and speed will be vc, and vc is nothing but critical velocity. So if this is the data, then the centripetal force will act on the satellite will be equal to mvc square upon r, where m is the satellite of the mass of the satellite, and vc is the critical velocity or the speed, and r is the distance of the here r is the orbital radius of the satellite from the center of the Earth. And this centripetal force is provided by the gravity of the Earth. Alright, so student, as the centripetal force is provided by the gravity of the Earth, therefore the centripetal force, that is mvc square upon r, is equals to the gravitational force of attraction between the Earth and the satellite. So the centripetal force is mvc square upon r plus h. So in our previous slide we have seen centripetal force is mvc square upon r. So r is nothing but the radius of the satellite. So that radius of the satellite will be equal to the sum of radius of the Earth plus height of the satellite above the Earth's surface. Okay, and the gravitational force between Earth and satellite will be equal to capital G m upon r plus h square, where g is the gravitational constant, capital M is the mass of the Earth, and small m is the mass of the satellite. Alright, so if you will solve it further, so m and m gets cancelled, r plus h and square will be cancelled, and the remaining term we will write will be vc square upon is equals to gm upon r plus h. So on taking square root, we will get vc is equals to under root of gm upon r plus h. So this is the This is a formula for critical velocity. Okay, so critical velocity depend upon the mass of the earth and r plus h. So here if you will look at the term that capital G is equals to the gravitational constant, and the value of this G is equals to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square, and capital M is the mass of the earth, and the value of mass of the earth is fixed, that is 6 into 10 raised to 24 kilogram, and the radius of the earth is also fixed, that is capital R, and the value of it is 6.4 into 10 to the power 6 meter, that is equals to 6400 kilometer. And small h is equals to height of the satellite above the earth's surface, and r plus h is equals to radius of the orbit of a satellite from the center of the earth. So it can be seen that the critical velocity does not depend on the mass of the satellite, but it is depend on the mass of the earth. Okay, and as the height of the satellite's orbit from the earth's surface increases, the critical velocity decreases. So student, I hope you all have understood this short derivation, or we can say the formula for how to drive the formula for critical velocity, that is VC. I hope you all have understood, and the next part we will study in our next video. Thank you.